All right. Firstly, I'd like to thank the organizers for giving me this great opportunity to talk in this commutative algebra and algebraic geometry seminar. So thank you so much. Today, I'm going to talk about the Gorenstein-ness of the endomorphism rings of ideas, which is based on the recent research jointly with Goto, EI, and Matsuoka. So if you are interested in this topic, you can find the paper in archive. I posted it in February last year. So if you're interested, then please check it. And in this talk, let me consider the following question. I mean, the question is very much simple. So take R to be a Noetherian local ring of positive depths. Then the question is, when is the endomorphism ring of the maximal ideal Gorenstein? So this is the question. What is the definition of Gorenstein when the ring isn't commutative? Is it the same? Yes, it is the same, I think so. And you can access the slide of my talk at the link. All right. So can I continue? To this problem, let me consider first the one-dimensional case. So suppose the dimension of R is 1, that means R is Koyama-Curry because the depth of R is positive. In this case, the endomorphism ring of the maximal ideal is Gorenstein if and only if the base ring R is almost Gorenstein and the embedding dimension is equal to the multiplicity. Here, V of R means the embedding dimension and the E of R is the multiplicity of the ring. And today, I think I have no time to explain the details about almost Gorenstein ring, but this is almost Gorenstein. So it's very close to the notion of Gorenstein rings. And this is due to Goto, Matsuoka, and in 2013, and they showed this theorem. So in this sense, we can understand when the endomorphism ring is Gorenstein. So next, how about the case where the dimension of R is at least 2? And it's very much well known that if the depth of R is at least 2, then the endomorphism ring is equal to the base ring R itself. So in this case, the M column M is Gorenstein if and only if R is Gorenstein. So, I mean, this observation tells us that we should consider the case where the dimension of R is at least 2 and the depth of R is 1. Okay, and to consider this question, the key ideas of our argument are the S2fications and the trace ideas. So before stating our main results, let me explain the basic properties of the S2fication and the trace ideas. So let's get started. So throughout my talk, let R be an arbitrary commutative Noetherian ring, and QR denotes the total ring of fractions, and we use HT to be the set of ideals which have height at least 2. And W means the set of non-zero divisors. Okay. With this setup, we fix a QR module V. And for an R submodule M, we define M tilde here to be the set of elements F in V such that I times F is contained in M for some ideal I which have height at least 2. And it's straightforward to show that M tilde is R submodule of V and which contains M. And we call this the S2ification. S2ification of M. All right, this is the definition. And now let me explain some basic properties of the S2ification. And first, if L is an R submodule of V and M is contained in L, means like L is an intermediate submodule between M and V, then taking the S2ification maintains the inclusion. So I mean, M tilde is contained in L tilde. This is, yeah, it's clear, right? By definition, we have this inclusion. And if we take the QR module V to be the total ring of fraction itself, if we take V to be QR and M to be R, so if we consider R tilde inside of the total ring of fraction, this is because of the definition, R tilde is an R submodule of QR, but in this case, R tilde is an intermediate ring between R and QR. So R tilde has a ring structure, and in this sense, M tilde is an R tilde submodule. This is by definition, we have this, right? And now let A be an element of R and N be an R module.
Sorry, can I ask you something, because I'm a little bit,
Sure.
In the definition of your S2ification,
Yes.
it sounds as if it's not depending on V, but you could take for V just M. So I'm missing something. I mean, like for instance, why is M tilde even an R tilde module?
Mm-hmm. Later, I will explain it. Thank you.
Okay.
Thank you. All right, and then the pair A and B. This is called any sequence if A is a non-zero divisor on N and B is a non-zero divisor on N mod AN. Here, I mean, any sequence does not mean n regular sequence. Here, we do not assume this condition. We just assume A is a non-zero divisor and B is a non-zero divisor on N mod AN. By using this notion, if the height of the ideal generated by A and B is at least 2, then this pair forms M tilde sequence. So let me show this. Because V is a module of QR, and M tilde is a submodule of V. That means a non-zero divisor on R is a non-zero divisor on M tilde. So to show this, we will check that this B is M tilde mod A M tilde non-zero divisor. To do this, take F in M tilde and assume that BF is in A M tilde. So we can write BF is equal to AG for some element G in M tilde. And by definition, we can choose ideas I and J in this set such that IF is containing M and JG is containing M. So IF plus JG is containing M. That is by definition. So by setting X to be F over A, this is equal to G over B, but by using this X, we have IA plus JB times X. This is exactly the same as this one, but this is containing M. So because I and J have height at least 2, so this ideal also has height at least 2. So X is containing M tilde. This means AB is M tilde sequence. Okay. So by using this lemma, we have the following proposition. So suppose that one of the following conditions is satisfied. Okay. Then M is equal to M tilde. I mean, we have this equality if and only if every pair with the height of this ideal is at least 2 is M sequence. And the implication from the left-hand side to right-hand side, this is this follows from the previous lemma. So to check the equivalent condition of this proposition, we need to prove the converse. So now assume M is not equal to M tilde and take an associated prime P in as Z. Take an associated prime P in this module. And because P is associated prime, we can write P is equal to M con F for some element F in M tilde. And by definition, we can choose ideal I such that IF is containing M. So that this means, I is containing M colon F. So I is containing P. Now, because if this condition is satisfied, then because F is in V, so F is in this set, that means we can choose a non-zero divisor A such that AF is containing M. And on the other hand, if the second condition is satisfied, then this means I is not contained in this set. This means I contains a non-zero divisor, right? I contains a non-zero divisor. This means AF is in IF, but IF is containing M. So in any case, we can choose a non-zero divisor A such that AF is containing M. So now, by using prime avoidance theorem, we can choose an element B in P such that the height of this ideal is at least 2. So by our assumption, this pair is M sequence. So by using snake lemma, we get this natural exact sequence. And now we consider the element BF is in M. We consider this element. This is in M, and consider the class of this element in Z here. The class of this element is equal to 0 in Z. So the image of this element is also 0, but the image of this element is equal to B times sigma of F bar, right? And because AB is M sequence, we get sigma of F bar is 0. But because sigma is injective, we get the class of F is 0 in Z. That means F is in M. But this is impossible because F is not in M. So this makes a contradiction. So we have M is equal to M tilde. And by using this proposition, we have the following corollary. So suppose that one of the following conditions is satisfied. Then the first one is M tilde tilde is equal to M tilde. And this is because by definition, M is contained in M tilde. And by, oh, sorry, we don't need this. Because this is because we just use the previous proposition, and because every pair with height at least 2 is M tilde sequence by this lemma. So by combining this lemma and this proposition, we get M tilde tilde is equal to M tilde. So we have this equality. And if we take L to be an intermediate submodule between M and V, and then, yeah, by definition, M, because M is contained in L, so M tilde is contained in L tilde, but by previous proposition shows, because every pair with height at least 2 is L sequence, so we have this equal. And I mean, the second, the assertion B says, I mean, M tilde is the smallest R submodule L, which satisfies the condition here, this condition, right? And by using this corollary, we have the following consequence. I mean, if R satisfies the cell condition S1, and if M tilde is finitely generated as an R module, then M tilde is the smallest R submodule of V, which contains M, and M tilde satisfies S. So in particular, if we take V to be QR and M to be R, then, I mean, if R satisfies S1 and R tilde is finitely generated, then R tilde is the smallest modular finite birational extension of R, which satisfies the series S2 condition. So that's why we call it the S2ification. And in particular, if R satisfies S2 condition, then because of this corollary, we get R is equal to R tilde, because R tilde is the smallest modular finite birational extension satisfying S2 condition, right? All right.
So what about this condition of finally generated, the tilde? What about the condition that M tilde or R tilde are finally generated? Is that, there must be general situations in which this is true, or not?
Sorry, the Wi-Fi connection is a little bit
okay.
strong.
So there is a condition if M tilde is finally generated.
Yes,
so
this is
how difficult is that to? Yeah.
This is a very good question. In general, there is an example that R tilde is not finitely generated, but if we yes, but yes, this is very good question. Yes, wait a minute. All right. Okay. We need a proof, but if R is a homomorphic image of a Gorenstein ring, and R is locally quasi-unmixed. Later, I will remind you the definition of quasi-unmixedness. Oh, I need one more. And S1. If R is a homomorphic image of a Gorenstein ring and R is locally quasi-unmixed, and S1. And I think one more condition we need. No, M is finitely generated. For safety, A is a finitely generated torsion-free R module. Then M tilde is a finitely generated. We need a proof, but
but okay, that's a fairly mild situation. I mean, I can live with that.
Mild situation, but yes, but in general, I think in general, R tilde is not finitely generated. There is an example, but if we assume this kind of mild conditions, then M tilde can be finitely generated. So thank you for your question. This is very important. All right. Now, in the rest of this section, we assume M is finitely generated and assume this condition, and V is phase-through. All right, we assume this. And now we consider for a non-zero divisor A, the primary decomposition of the module AM, where QP is a P primary component, and we set U of AM means the unmixed component, which is by definition this, which is equal to M if AM is equal to M, and otherwise the unmixed components is the intersection of P primary component where P is in the minimal prime. All right, yes. Then we have the following theorem. Okay. Okay. Because of the time consideration, let me skip this proof. If the time permits, let's go back to the proof. But the point is, I mean, let A be a non-zero divisor and M is M. M over A is in M tilde if and only if M is in the unmixed component. So by using this theorem, that we get if M tilde is contained in M over A, then M tilde is equal to, I mean, M tilde have this form. This is the point. Okay, this is the basic property of esterification. Now let's discuss the notion of trace ideas. Still R denotes a commutative Noetherian ring. And consider two modules, M and X, and consider the natural homomorphism from hom mx tensored by M to X, which sends F tensored by M to F of M. This is natural homomorphism. And we set TR sub X sub M to be the image of this map and call it the trace module of M in X. Then Endo proved the following proposition. I mean, the following conditions are equivalent for an ideal. The first condition is I is a trace ideal. Trace ideal means I is equal to trace R of M for some module. This is a definition of trace ideal, but this condition is equivalent to saying that we can choose M. Oh, sorry, we can choose I. No, we can choose M to be this mod. Sorry, I is trace if and only if I is equal to trace of I. So we can choose M to be the ideal I itself. And also, this condition is equivalent to saying that this natural embedding induces the isomorphism of R modules between these homs. So hom II is isomorphic to hom IR. So if when I contains a non-zero divisor, I mean, hom II is isomorphic to I colon I. So we consider the column inside. We consider the column in the total ring of fraction, right? And also hom IR is isomorphic to R colon I. So when I contains a non-zero divisor, we can add this condition. Okay. Yes, this is the very basic properties of trace ideas. All right. So let's move to our main results. To state our main results, we begin with the following lemma. To state this, firstly, let me recall the definition of unmixed and quasi-unmixedness of a local ring. I mean, for a local Noetherian ring, we set as H of A or Ash H to be the set of prime ideas P such that the dimension of A mod P is equal to the dimension of A. And it's known that this is contained in the minimal prime of A. And then A is called unmixed if the associated prime of the completion is equal to as H of the completion. So now we consider the completion. And unmixed means we have this equality. And quasi-unmixed means we have this equality. Minimal prime of the completion is equal to the as H of the completion. This is the definition. Then we have the following lemma. So let A be an Noetherian ring and let B be a modular finite birational extension, and let I be an ideal of B such that I is contained in A. That means I is an ideal of A also. And as an ideal of A, I has height at least 2. If the ring is locally quasi-unmixed, locally quasi-unmixed means every prime ideal A, the localization, the local ring, this is quasi-unmixed. Locally quasi-unmixed means every localization at the prime ideal is quasi-unmixed. and B satisfies the sales S2 condition, then I is a trace ideal. And B is equal to icon I. The proof is like this. If A is locally quasi-unmixed, then by Ratliff, we get the height of P is equal to height of P intersection A for every prime in B. So because I has height at least 2, this means the height of I as an ideal of P is also at least 2. Then because B satisfies the sales S2 condition, we get the grade of I is at least 2. So I contains a B regular sequence of length 2. We get B is equal to I colon I. Also, B is equal to B colon I. So because A colon I is contained in B colon I, and I colon I is contained in A colon I. So we get I colon I is equal to A colon I. This means I is a trace idea. So this is the proof. And the key point of our argument is the following, but the proof is a little bit complicated and rather technical. So today, let me skip the proof. But this is the key point. And by using this proposition, we have the following corollary. Can you see? Consider a Noetherian local ring and be module finite birational extension. And we assume these 3 conditions. A is quasi-unmixed, and the height of this ideal R. A colon B is at least 2, and B is Gorenstein. Then we have this. B is equal to the esterification, and B is Koyama-Curry. This ideal is trace, and B is equal to R colon R. And the ring A has the canonical module, which is isomorphic to B. And finally, A is equal to B if and only if A is Koyama-Curry. We have this corollary. Let me check it. Yes. Because, yes, by this lemma 4.1, because A is quasi-mixed, and because B is Gorenstein, so B satisfies S2. And height of this ideal R is at least 2. So by this lemma, we get B is equal to R colon R, and R is a trace idea. And also B, because the ring is quasi-unmixed, so we have this equality here. So every system of parameters of A is a regular sequence on B. That means depth of B is equal to D. Now we consider C to be B over B mod A. Then because this ideal R is contained in the annihilator of C, and the height of R is at least 2. So this shows the dimension of C is at most D minus 2. And then by taking the local homology functor, we have this isomorphism. So by taking the matrix dual, we get the canonical module of the completion is isomorphic to A hat tensor by B. So the canonical module of A exists, and this is isomorphic to B. Okay. And also because B is equal to R colon R means B is equal to R. And this is R is an ideal of A also. So because height of R is at least 2. So by definition, B is contained in A tilde. And also because A is contained in B, so A tilde is contained in B tilde. And because B satisfies S2, we have this equality. So B is the esterification. And for the last statement here, because if A is equal to B, because B is Gorenstein, A is clearly Koyama-Cory. So let me show the converse implication. So suppose A is Koyama-Cory, then because we have this natural exact sequence. And the B is isomorphic to the canonical module. So the depth of A is D, and the depth of B is also D. So the depth lemma shows the depth of C is at least D minus 1. So this shows the cokernel should be 0 because the dimension is at most D minus 2, and the depth is at least D minus 1. So we have C 0. That means A is equal to B. This is a proof of this corollary. Yes. So we now state our main result. Sorry. The main result is consider an Italian local ring and assume that A is quasi-mixed. Then the endomorphism ring of I is Gorenstein if and only if I is trace and the canonical module is Koyama-Cory, and there exists this kind of exact sequence. And this condition is also equivalent to saying that B is Koyama-Cory and A has the canonical module, which is isomorphic to B. Yes. To show this, the implication from 1 to 3, this is because yes, by previous corollary, we have the implication from 1 to 3 because yes, because I is contained in R. And by our assumption, ideal I has height at least 2. So the ideal R has height at least 2. So by this corollary, we get the implication from 1 to 3. And yes. And the implication from 2 to 1, this is because of this proposition here. Because if the canonical module is Koyama-Cory, then by this proposition, we get A tilde is Gorenstein. And also because I is trace. So by this proposition, we get A tilde is equal to I colon I. So if we assume the canonical module is Koyama-Cory and I is trace ideal, then A tilde is equal to I colon I, and this is Gorenstein. So the ring B is Gorenstein. So we have the implication from 2 to 1. And finally, we check the implication from 3 to 2, but by our assumption, our ring B is Koyama-Cory. So the grade of B is equal to height of, the grade of I is equal to the height of I. And because A is quasi-mixed and I has height at least 2. I have height at least 2. So by this lemma, we have I is a trace idea, and also this natural exact sequence is a required sequence because B is isomorphic to the canonical module, and because I is contained in A colon B. So this exact sequence gives this required sequence. So this is the proof of our main theorem. And as a corollary, if we do not assume quasi-unmixedness of A, we have the following. So, I mean, instead of the quasi-unmixedness of the base ring, we add this condition. So, I mean, let A be an Italian local ring and the Eisen ideal of A with height at least 2. Then the following 3 conditions are equivalent. The first condition is B is Gorenstein ring and A is a homomorphic image of a Koyama-Cory ring, and as associate, minimal prime is equal to as H of A. And the second and third condition are the same as the main theorem. So the difference is only this part. Yes. So yeah, we have this corollary by using the theorem of Kawasaki's arithmetic Kawasaki's arithmetic macroification theorem. We have this corollary. Sorry, I have no time to explain the details, but we have this. All right, let's move to our next section. And in this section, as an application of our theory, we consider the Gorenstein-ness of the Riesz algebras of powers of parameter ideas. So let A be an Italian local ring with dimension D and the depth T. And as you know, but for each ideal I in A, we set R to be the A subalgebra of the polynomial ring generated by I times T. And this is called the Riesz algebra of I. And if the base ring is Koyama-Cory, then the Koyama-Cory and the Gorenstein properties of the Riesz algebras are well explored. There are many, many results. However, I mean, even if A is not Koyama-Cory, the ring A contains an ideal whose Riesz algebra is Gorenstein. For example, look at the example given by Hoxha-Roberts in 1974. So let A be K adjoint X squared Y X cubed and XY in the two-dimensional formal power series ring over field K. And let Q to be the ideal generated by X squared and Y. Then the ring A is not Koyama-Cory because Y X squared, this system of parameter is not a regular sequence. So A is not Koyama-Cory, but the Riesz algebra of the square of Q. This is Gorenstein. And yes. And Shimoda, he was very much interested in this example, and he gave the following result, which is a generalization of this example. This is unpublished result of Shimoda around 30 years ago, and he proved this theorem in his seminar talk at Meiji University, but this is his result. So suppose A is two-dimensional and the depth of A is 1, and that could be a parameter idea. Then the Gorenstein nest of the Ries algebra of Q squared, this condition is characterized by the properties of A and B, the system of parameters, like A, B are non-zero divisors, and the intersection of these column ideas is equal to A column B. And A mod this ideal is Gorenstein. So by his result, I mean, we get the following question naturally. So, I mean, the question is, when is the Ries algebra of powers of parameter ideal is Gorenstein? And I mean, for me, it's a little bit surprised, but if the base ring is Koyama-Cory, then the Ries algebra of powers of this parameter ideal is not a Gorenstein ring, because this is because the A invariant of the associated graded ring is -1. If this Ries algebra is Gorenstein, then by the result of Goto Nishida or Goto Shimoda or Ikeda, we get if this is Gorenstein, then the A invariant should be -2. But in this case, the A invariant is -1, so that means the Ries algebra cannot be Gorenstein. However, still we have an example that the Ries algebra is Gorenstein if A is not Koyama-Cory. So it was mysterious for me and very much interested in this kind of phenomenon. And recently, Goto and EI are interested in Shimoda's result, and they gave a complete generalization of Shimoda's result. I mean, so they proved this theorem. Suppose the local homology is 0 except 1 and D, and the H1 is finitely generated. Then the Ries algebra is Gorenstein if and only if the H1 is non-zero. That means the depth of A is 1. And the Koyama-Cory type of H1 is equal to 1, and the annihilator of H1 is equal to the sum of the unmixed component. And when this is the case, the esterification is Gorenstein. They prove this result, and which is a complete generalization of Shimoda's result. And when I saw this theorem, yeah, it's very nice and very beautiful characterization. But however, I feel like that, then how do we check the second condition? I mean, for a given concrete example, how do we check the second assertion? So motivated by this observation, we get the following result. So let A be a Noetherian complete local ring, and assume that the depth of A is 1. Then the endomorphism ring of an imprimary ideal I is, assume these three conditions. The endomorphism ring is Gorenstein, and the Koyama-Cory type of B mod A is 1, and the ideal R is generated by the elements. Then the Ries algebra is Gorenstein. this is a consequence of this theorem and our main result. Combining our main result and this theorem, we get this theorem. I prepared a proof, but because of the time consideration, we should skip this proof. All right, finally, let me give some examples. All right, the first example is like this. Let S be a Gorenstein complete local ring and assume that S contains a field K. Now we take a parameter ideal Q such that Q is not equal to the maximal ideal. And we set A to be K plus Q. This has a ring structure and Q is a maximal ideal. And we need a proof, but in this case, the ring A is Noetherian complete local ring of dimension D and the depth 1. And also, if the length of S mod Q is 2, then all the assumptions of this theorem are satisfied. So the Ries algebra is a Gorenstein ring. So for example, now we consider S to be the formal process ring and the Q to be the ideal generated by x1 squared x2 through xd. Then because the length of S mod Q is 2, so the Ries algebra is Gorenstein. And A is not Koyama-Cory. This is the first example. And also, now we consider the formal process ring with 2 variables, and let P be the numerical semigroup ring. Sorry. Numerical semigroup ring. And we assume that H is symmetric, means this numerical semigroup ring is Gorenstein. And yes, and now we consider A to be P plus SB. This has also ring structure, and yeah, we need a proof, but this A is Noetherian complete local ring with of dimension 2 and the depth 1. Yes. And we set Q to be the ideal generated by T to C and S, where C is the conductor of H, which is equal to, I mean, because P column V, this is an ideal of this DVR. So we can write P column V is equal to T to the C times V by using this. Yeah, we need a proof, but then we can show this. The Ries algebra is Gorenstein. Yes, and finally, consider a Gorenstein complete local ring and Q to be a parameter ideal, and let A to be the fiber product of S and S over S mod Q, which is by definition, this is a set of elements X comma Y in the directed product of S, such that the class of X and class of Y are the same in this ring. Then this fiber product is a Noetherian complete local ring of dimension D and depth 1. And now we consider Q to be the ideal generated by alpha 1 through alpha D, where alpha I is this element. And then this Q is a parameter ideal. And all the assumptions of our theorem are satisfied. So the Ries algebra is Gorenstein. So finally, let's consider U to be the formal partial ring with 2D variables, and let A be U mod this intersection of ideals, which is naturally isomorphic to the fiber product of S over K. Now we consider Zi to be the image of Xi plus Yi, the sum of variables in. And we consider the image in A. Then the ideal generated by Z1 through ZD is a parameter ideal of A, and we get the least algebra of Q to the D is Gorenstein. So by our result, we can construct many examples of the ring and the parameter ideal Q, such that the least algebra of Q to the D is Gorenstein. So maybe we should stop here. So thank you for your attention.
Thank you.
Thank you.
Thank you, thank you. And I see that there were a few questions already in the chat.
The equalities. Oh, this is because I contains non-zero divisor. I mean, yeah. So we consider the column in the total go fractions. So this is the definition. And yeah, we need the assumption that I contains a non-zero divisor, but yeah, because how should we say? Take on element X, X goes X hat. This gives an isomorphism naturally.
X hat is multiplication by X?
I think so, maybe.
How do we know that it's surjective? The thing I've been worried about is how do we know it's surjective?
It's the image of that non-zero divisor, I think, determines everything else.
Okay.
And
yeah, because it's the
yeah.
It's invertible, so then you get the image of one. It's invertible in Q, so then you get the image of one.
Yes.
That's the point.
All right, thank you. And the completion. Could you remind me the equidimensional?
Oh, I was just wondering if it was the same, like it was just another word for the same thing. I think of equidimensional as meaning that all of the chains of maximal prime, the maximal chains of prime ideals have the same cardinality, I mean length. So that seemed to me like it was the same condition, right? Because you're saying that all the minimals are, if you mod out by them, you're the same dimension as the rig. You don't, there's no minimal of that if you mod out by it, you're lower the dimension. So that seems to imply that the minimals all have the property that the chain, the maximal chain from the minimal to the top is the same length, right? So I was just checking my understanding of the definition. And so I think that means that all chains, you said that the condition applied in the completion, not in
Yes.
the original ring, right?
Right.
So that's the statement that in the completion, all of the fully saturated chains of primes are the same length, right? Am I understanding right?
Yes.
Okay.
Thank you.
Thank you very much.
Thank you.
Something's still bothering me about the colon equality with the endomorphism ring, but I'll think about it later. Thank you so much.
Thank you.
I think, Ben, is classical. I'm sure is in the literature. I know we have been using it many times. So it's one of those things of basic commutative algebra that we took the course, and now we need to go back to look at the details.
I figured it was a completely standard thing that I've even probably read at some point and forgot, but it was really bothering me because that was why I retrospectively, like, I don't even, the question at the beginning about non-commutative Gorenstein rings, that might not even be a real definition. I only asked because you were talking about endomorphism rings, so I assume they're not commutative, but actually in the present case, based on this, they are commutative. So that definition, I apologize for that question because it was a distraction.
Thank you for your question.
And see, like for me, I am used to work mostly on Cohen-Macaulay rings, so the canonical module, automatically maximal Cohen-Macaulay. So I also had a moment to think, in general, the canonical module may not even be Cohen-Macaulay.
Right. That's the point.
That's something I know I need to be very careful about. In non-Cohen-Macaulay. It's so stuck in my mind, that is part of the definition of being maximal Cohen-Macaulay.
I actually have a question about that. One of your theorems, actually your main theorem, I think, your main condition is about the Gorensteinness of, can you pull, can someone switch? Okay. Right. So that in the condition 2, which seems to me like an intermediate condition, it's a technical condition, but I is the point I says that there your canonical module is a Cohen-Macaulay module. So in other words, this is a ring that has a small Cohen-Macaulay module, which is a problem that we still don't know. Which rings have small Cohen-Macaulay modules? That surprised me a little bit. And so, so this means to me that you're proving that a ring that satisfies your theorem admits a small Cohen-Macaulay module, a finally generated module which is Cohen-Macaulay. And that's an open problem. We don't know whether every no-theorem local ring has such a problem. Well, in fact, it doesn't. It has to be complete. So in order to, the conjecture says it has to be complete. There are counterexamples in the non-complete case. So I find it a bit puzzling, that result that you have there. It's clearly stronger than you have more. I mean, so the condition is clearly, it's not always going to happen, but it is still, I think, if you consider that corollary, actually, that you have a well, of course, I mean, you condition, you get more than just that you have a Cohen-Macaulay module. You have actually, I don't know what to call that. You have even a finally generated Gorenstein algebra, namely B, becomes is an algebra. And it's finally generated.
Where's the conclusion that it's finally generated?
Well, Ka is a Cohen-Macaulay module. Ka is the dual module.
Canonical module.
Sorry, thank you. It's a canonical module which is always assumed to be finally generated, and B is isomorphic to it. So it's the finally generation of B is something that comes from the theorem.
I see.
Well, it's interesting. Even if you don't know what to say about it, it's still a nice result.
Yeah, thank you for your question.
Any other question?
Do you have tried with the change of rings? I mean, if we have a homomorphism between two local Noetherian rings from R to S, Rm and Sn, if we have endomorphism of N is Gorenstein, can we say that endomorphism of M is Gorenstein? Because with the properties that you have, maybe it's not hard to work on this, you know, somehow extending this for the change of ring.
Yeah, thank you. That's a good question. I see. Yeah, actually, I never thought about this, but yeah.
Yeah, and we have endomorphism of N is Gorenstein. Then can we say that endomorphism of M is Gorenstein? Then you have some condition for S, and then you will get the properties for R.
Yeah, like flat or something like that.
I see.
That's very classical question that the people ask.
Yeah, but very much interesting. Yeah, it's very much interesting for me.
From the properties, I think it's not hard to prove this one, you know, because we know many things from S to R. For example, Gorensteinness of S, of course, transfer to Gorensteinness of R. And some other things like the canonical modules and the So.
Yes.
That's okay. Maybe this is a question to think about.
I'll think about this. Thank you. Later. Thank you.
Endo, we cannot expect you at 5 o'clock in the morning to answer all our questions. That is too much.
Thank you.
So anybody, any more questions? Thank you for sharing the slides and for a very nice talk.